Swayam Prabha. Digital India. Educated India.
So, in the last lecture, we saw a setting of distance relays. We saw the setting of zone 1, zone 2 and zone 3. One particular aspect of zone 1 which you must have noticed is that it does not cover the entire line. So, we'll just quickly recap, because this is what we are going to discuss in today's class. So, assume that this is the line that we are seeing between sending end and receiving end, and the relay here is say R1 and the relay here is R2. This relay covers about 75 to 80% of the line, sometimes 85, while this relay covers in its zone 1. This is zone 1, I should mention zone 1. The other overlapping zones, etc., and the extension of zone 2 to cover 50% of the next line or 20% as the case may be, and the extension of zone 3 to cover 200% of the next longest line. All that we have seen in the previous lecture. But if you see here, this part of the line, maybe 15 to 20 or percent, is the primary protection here has slowed down. Now, transmission lines at extra high voltages, 132 kV, 220 kV, 400 kV, even 765 kV, the primary protection is indeed distance protection. Even now, though for shorter lines, current differential protection is now being used as the primary protection. But coming back to distance protection, it is not very desirable to leave a fault here, so to say, hanging for the zone 2 time. So, maybe whatever 200 milliseconds, 250 milliseconds or 300 milliseconds. So, what can be done? One way I said of overcoming this is to use the information from this end here, from the suppose we are talking of the sending end S, then the relay R2 or some other information there from that end can be used to speed up the decision for this part. Using of information means, of course, various things. You could use the current information there, or you could use the just the phase information there, or you could use some other information. But what is common is it will require some means of communication, which is known as pilot wire communication. Of course, you could use the transmission line itself, since it is connected between the ends and between the ends S and R. You could use the transmission line itself, in which case it is known as power line carrier communication. We saw part of it when we saw the CCVT part, but here specifically a separate wire is used, which is known as a pilot wire. So, depending on the usage of the various quantities and the pilot wire, there are different types of protection. We will not see everything here. We will see only those related to distance relaying. Some part like current differential and others we will see in the later part of the course. So, for classification purposes, we will mention all, and then we will look at only those which are relevant to distance protection. So, pilot system classification. Pilot means a wire which will be run between the two ends, but which is not used for the power transmission. It is used only for the purposes of communication. So, that is why it is known as pilot. It is classification. Okay. So, depending on whether the communication channel is required or not required, whether the power flow direction is in what direction. So, depending on all these quantities, the systems are classified. One is the first one, of course, is channel required for communication. For tripping operations. It is known as blocking. I am sorry, this is channel required for tripping operations is known as transfer trip. Transfer trip. Channel not required for tripping operations is known as blocking. Okay. The second one, of course, this could be, if this is say A, B could be fault detector principle. Detector principle. If it is based on power flow direction, then it is known as directional comparison. Whether the power is flowing into the bus or out of the bus. Then if it is based on relative phase position of the currents, of the currents, it is known as phase comparison. Okay. And then the third, though we will not discuss that here, it is wave deflection from a fault. So, this is based on the travelling wave principle. We are aware of how travelling waves are set up, and there are a few relays available in the market, very few, which are based on this, and they are very high speed relays. We may not discuss this in this course. If there is a little bit of time available, maybe we will just have a short lecture on this wave deflection. But otherwise, this is very special because it requires knowledge of transients, etc. We may not discuss this in this course. Okay. So, now depending on the combination of fault detector principle and whether channel is required or not required, the protection scheme, the pilot wire protection scheme is described by a combination of the above features. We will see, we will discuss 3-4 schemes today. Okay. So, now there are other schemes like directional comparison schemes, like directional comparison blocking, directional comparison unblocking, overreaching transfer trip. So, depending on how the features are combined, we will have, we will see these today, directional comparison systems. Okay. So, these are directional comparison these we will be studying today, directional comparison unblocking, then 3 overreaching transfer trip. These terms will become clear as we discuss the schemes today. Then there is an underreaching transfer trip. Overreaching and underreaching is the same concept that we discussed in distance relaying with in-feed, out-feed, etc. The concept is whether the relay sees more impedance than what it is supposed to see and less impedance. So, in that the overreach and underreach are the definitions are the same. Transfer trip. This is further classified into permissive and non-permissive. The second one, which we will not be discussing today for sure, is current based systems. We will discuss this at some later date. So, this is current differential, in which case you compare the phasors from both the ends. You will require, since it is a transmission line, we will require relays at both the ends and then compare the two. Here this is further classified into pilot wire and digital. Again, all this is being mentioned for sake of completeness. We may or may not visit all of this again. And then there is the last one is phase comparison. So, this includes single phase, dual phase, segregated phase. The earliest way of because today we have GPS and then we use DFT and we compute the phasors, and then it is easy to compare phase angles. But these schemes have been used since almost 100 years now. So, that time there was no GPS and you could not compare phase angles directly. So, one thing that could be compared was the zero crossing. So, I mean just as a concept, not getting into too much of detail, if you convert the sine wave into a square wave and then send the zero crossing information to the other end, in essence of the comparison of the phase is just a comparison of the zero crossings. So, you could compare the zero crossing. Now, this could be done in various ways. Just send us the information of a single phase, or send a composite phase, or send two phases, or send each phase differently. So, A, B, C, and then the most accurate one of course was the segregated phase. But again, we are not discussing all that in detail today. I have just given an overview, so for the sake of completeness. So, we will now look at some of the pilot wire schemes, protection schemes, and the first ones that we listed here under A here. Some of them we will look at, and then we will go on to some other topic in distance relaying. So, this is what we completed last time. That was just a summary of what we did last time. Now, we look at pilot wire schemes. So, these four schemes actually we will look at: directional comparison blocking, directional comparison unblocking, then directional overreaching transfer trip, and underreaching transfer trip. I will also talk briefly about a variation of underreaching transfer trip, which is the zone acceleration scheme. Okay. So, as we discussed very briefly at the beginning of this class, that to provide high speed protection, simultaneous protection to both ends of the line, to 100% for the 100% of the line, we use these pilot wire schemes. Basically we use the information from the other end. So that the balanced 15 or to 20% of the line, which is the primary protection, is slowed down at that, we can increase the speed and then provide fast response for the 100% of the line. So, the effect is of course that it allows quick clearance of the fault at even towards the remote end of the line. So, these are the commonly used schemes out of the schemes that I listed down. So, these are the commonly used schemes. We will quickly look at them. Some of them, as more and more advanced communication schemes etc. have become available, some of them are redundant, but these schemes are still in use because the legacy legacy systems are still in use. You don't discard them so easily. They have served you well over a long period of time. So they are in use. So it is useful to know what these commonly used schemes are. Rather, the concept behind these commonly used schemes. So this scheme, the first one that we are discussing, the directional comparison unblocking, is actually one of the oldest schemes that has been in existence almost since 1930, so almost for 100 years now. And I mean, one of the first pilot wire schemes that came into existence here. So what this scheme does is, as you can see on the slide, it uses what are known as fault detectors and carrier start signals. The FD1 and FD2 that you see at ends A and B are the fault detectors. Okay? These are basically nothing but zone 2 distance relays, which are acting only as fault detectors. They are not tripping anything, but they will pick up if there is a fault beyond the remote end of the line, depending on how you configure them. But it will reach beyond the remote ends. So these are basically zone 2 of distance relays. Then you have the carrier starts signals, which are S1 and S2 as can be seen on the slide, and these are directional overcurrent elements, sensitive directional overcurrent elements, which will pick up for faults which will pick up for faults beyond the for example, it will reach beyond the fault detector. For example, here if you see for bus B, the S2 will reach beyond the FD1, and similarly S1 will reach beyond FD2. So it will reach almost to the remote end of the next line. Okay. So here the fault detector, as the name says, is used to detect fault in the direction of the primary line. So for FD1 will pick up for fault F1 as well as for fault F2. Similarly, FD2 will pick up for fault F1 as well as fault F3. So what it does is, it will use information from the carrier starts S1 and S2 to determine whether the fault is on the primary line or no. Okay. So the relays S1 and the relays R1 and R2 will have both the fault detector and the carrier start signals coming to them, and they will be enabled or disabled accordingly. Okay. So now just as an example, here if there is a fault at F2, or the fault F2 occurs beyond the bus B, then what will happen is FD1 will pick up, but the S2 will also pick up and the carrier will start, and then this relay here will not operate in zone 1 time. So, but however, if there is a fault at F1, then FD1 will pick up as well as FD2 will pick up, and S1, neither S1 nor S2 will pick up. Okay. So S2 will not pick up, and there is no carrier start received at R1, and hence it is free to trip in almost zone 1 time. Okay. It is not zone, because this carrier start etc. receiving the signal will take some time, but it is definitely much faster than zone 2. So this depends on the two elements, fault detector and carrier start, to either initiate the tripping or block the tripping. On the other hand, the next scheme is the directional comparison unblocking scheme. Here there is no carrier start, unlike the earlier scheme. Here there are no carrier start elements here. The FD1 and FD2 elements are the same, but S1 and S2 are not present. Okay. So here what happens is, the carrier channel is not continuously required. What happens is that the relays, it is assumed that all the faults are will be in zone 2. So what will happen is, the relays are kept in the block state. Okay. So only if the fault is on the primary section of the line, then an unblock signal is sent to the remote end. So, if there is a fault at F2, then FD1 will pick up, but because FD2 has not picked up, there is no unblock signal sent to R1. However, if there is a fault on R1, then FD1 picks up and FD2 also picks up. So, there is an unblock signal sent to R1 and it will operate in again in almost zone 1 time. So, if for a fault on the primary section, the relays will trip almost immediately. However, for remote faults or faults beyond the remote bus, the normal zone 2 operation will be initiated. Sorry. So, here this system is slightly in concept different. The next system, it is known as a directional comparison overreaching transfer trip. Okay. Here there is no block or unblock signal, but a trip signal directly is initiated, and in this case it is ANDed. Okay. So, similar to the earlier scheme, if there is a fault on the line, then these two fault detectors both will pick up, and at R1 they will be ANDed. Okay. So, if both are trip, then this a trip signal will be trip decision will be initiated for the primary line, and both will relays R1 and R2 will trip simultaneously. However, if there is a fault beyond the remote end, then only one will pick up, and since there is no ANDing of the trip mode, the trip will not be initiated in zone 1 time. It will, whatever is the normal zone 2 time or zone 2 operation will still hold good. The last scheme we discuss is a variation, not a variation, it is a different scheme altogether. I am sorry to have used the word variation. Is that it is an underreaching transfer trip. Means the FD1, here the fault detectors were set in like zone 2, here they will be set like zone 1 only, but they will not, they will be overlapping, but not reach to the remote terminal. So, here there is instead of an OR, the trip modes are, instead of an AND, the trip modes are OR, a logical OR is done. If either FD1 or FD2 picks up, then the trip is initiated. What will happen is inside of the overlap area, both FD1 and FD2 will pick up. Outside of the overlap area, either FD1 will pick up or FD2 will pick up. I mean, in the primary zone itself. Take for example, the fault very close to the R2, that is beyond the zone 1 of the relay R1, in which case FD2 will still pick up because it is still in, it still sees it in its zone. So, at R1, since we have ORed the trip modes of FD1 and FD2, at least one here in this case FD2 trip mode is on. So, it is still a trip is initiated. So, a fast trip or a trip in zone 1 time is still received. This is also a variation of this is also known as a zone acceleration scheme, where simply if FD1 picks up, the zone 2 timing is set to zone 1. It is very similar. So, I am not confusing you with terminology, but remember that there is a slight difference in how it is implemented. So, directional comparison underreaching transfer trip, a variation is zone acceleration, which is very popular and very commonly used. Okay. So, as a summary, we have discussed directional comparison blocking, unblocking, overreaching transfer trip and underreaching transfer trip. There are variations like permissive, non-permissive, permissive overreaching transfer trip, permissive underreaching transfer trip, but we are not getting into that, we are just discussing the principles, because we are not discussing the actual engineering, etc. There are differences and nuances in how the schemes are implemented. So, that is why, plus how the communication channels are used, whether FSK is used or normal guard mode is used, etc. So, I mean, it will take a few lectures to cover only these schemes. So, that is why we are not going into much detail, but we have covered the concepts. Now, we move on to another important part of rather not a part of distance relaying. This is a feature which affects the distance relaying, and that is what happens or how does a distance relay see a power swing. Okay. One reason why we discussed pilot protection before we discussed power swings is that though the pilot wire schemes will speed up the distance relaying decision, it will still not cover some faults that are there with distance relaying. It's like there is a genetic fault. Some families, they have diabetes runs in the family, or there is a problem with the eyes. Even small kids get spectacles at an early age. So those genetic faults may be difficult to overcome. Similarly, there are some I wouldn't say genetic faults. The way the distance relay is implemented, that itself gives rise to certain vulnerabilities. Like we saw load encroachment in the last lecture. We will see another, that is the power swing today. Okay, we are all familiar with power swings, but however, we will have a short recap of power swing. You must have studied it in some power system class, but just for the sake of continuity and completeness, we will have a look at it today also. So today this particular topic, we will see what power swings are. We will see the application of that to distance relaying through a two-area system, and then what happens to the power swing locus, how the distance relay sees this power swing or the impedance locus, and then we will see what some concepts of electrical center and how that affects distance relaying, how that is similar to a fault, and then we conclude. Maybe the electrical center and some other small topics we may not be able to cover in this lecture, but we will see it in the next lecture before we conclude distance relaying. Okay, so what is basically a power swing? A power swing is the oscillation in the real and reactive powers that are flowing on the line. Okay, they will actually oscillate. If you see three-phase power in a line, it should be constant, but when there is a power swing, it will oscillate. Now, these are usually the consequence of a large system disturbance like a fault. However, having said that, they could also be they could also be a consequence of some problems in your control systems like an AVR. So it could lead to hunting, and that could lead to some power oscillations. But here now we are now focusing only on the large disturbance like faults. So what happens after the fault is that due to the power swing, the encroachment of the distance relay characteristic could happen. Okay, we will see that the power swing on the P delta plane and how it looks on the RX plane, and then we will see how that once the impedance locus comes into the distance relay characteristic, there is no way for the distance relay characteristic to make out whether it is. There are ways, of course, like power swing blockers, that we will see maybe in the next class. But once it comes into the distance relay characteristic, the distance relay will think that it is a fault, and then it will issue a trip when there is no fault. Okay, so it may make a bad situation, already bad situation, even worse. Okay, so this is what it says. So that the impedance trajectory, if it stays in the relay zone for for a sufficiently long time means whatever your zone 2 or zone 3 timer is. If it comes into zone 1, then there is an immediate trip decision anyway. Okay. So, here this is our commonly discussed two area system. You have the only difference here is that you may be very familiar with this system, but the only difference here is that we have introduced a relay here also, because we want to see the effects of that swing on the relay. So, that is why we have introduced a relay here at the bus A, as you can see on the slide. And there are two, the power system as such has been divided, has been modeled as a two area system, where one side is the source is ES angle delta, and the other side is ER angle 0, which is the reference phasor here, and the difference between them is the phase angle difference between ES and ER, or the two sources, is delta degrees or radians in this case. The machines have been modeled with or the sources rather have been modeled with internal impedances ZS on this side and ZR on the other side, and the line has a impedance ZL. Okay. So, now what happens when there is a fault? Okay, this is a single line here. So, when there is a fault on that line, we are assuming a solid fault. So, there is no power transfer possible, and the power transfer goes to 0. Initially, as you can see on the P versus delta curve here, the x axis is delta, the y axis is P, and initially it is operating at this point here, the red dot that I have shown. When there is a fault, the power transfer goes to 0, and the initial angle of course is delta naught, and the mechanical power input is PM naught, okay, and it intersects at this point, and this is the stable operating point here. Now, when there is a fault, the electrical power goes to 0, okay, and what happens is the mechanical input is still on, the turbine, the steam turbine or the hydro turbine, the mechanical input is still on. So, the and the electrical output is 0. So, if you remember the equation here, it is there here. Actually, it is Pm minus Pe, 2H by omega H, H2 d2 delta by dt2 is equal to Pm minus P. The initial angle is Pm naught, the initial the mechanical input is Pm naught, and Pe has gone to 0. So, what happens is that the machine will start accelerating and the delta will go on increasing. Till what time? Till delta 1 or delta clearing, wherever the fault is cleared. Okay. And then this area, which is that Pm minus Pe and the rectangle between that, between Pm and 0 and delta naught and delta 1, that is the area is known as the accelerating area, and that because that is the input available to the rotor to accelerate. And then once the fault is cleared, it will the operating point will shift from 0 power to some point here. Okay. But now what happens is the electrical power here is greater than the mechanical input. Okay. So, the rotor which was accelerating now will start slowing down. Okay. It will not slow down immediately, but since the now there is a decelerating force or torque on the rotor, it will start decelerating, and then it will slow down, and it will but the acceleration is slowing down. So, it will move around along this and come to some point here, which is delta max, that is the maximum angle of the swing. Okay. And then because the input now is negative, it will start swinging back. Okay. Ideally, it should have stopped at this point here, okay, but it will not, because it is still swinging back. So, it will go here in this direction here. Okay. And now what happens is the mechanical power is more than the electrical power. Okay. So, the process will reverse and then it will start accelerating again, and it will actually if there is no damping, then it will keep on swinging between these 2 points here, okay, infinitely. Okay. But fortunately, we have damping due to electrical and mechanical forces or mechanical components. We have damper bars in the poles, etc. So, what will happen is slowly the oscillations will reduce and eventually it will settle down to this original operating point. Okay. Now, how these oscillations appear, now this is a P delta curve, how these oscillations appear on our Rx plane is interest, but how we will I mean we will go through that step here. We will first complete a few details on this P delta curve itself. Okay. So, now what happens if this delta max is such that it goes beyond 180 minus delta naught. Okay. If it goes beyond this point here, then what will happen is the electrical power will again become less than the mechanical power, and the acceleration will continue. Okay. And then eventually it will go beyond 180 degrees and the machine goes out of step. Okay. So, it is very essential that you clear the fault early. That this is another reason why fault clearing times should be fast enough, so that you get enough decelerating area here to compensate for the accelerating area here. So, delta max has to definitely be less than 180 minus delta naught. And how do you find delta 1 here? You have to you find from the clearing time here. Okay, you find it from this equation here. You integrate this equation twice. Okay, and then from that you will be able to find the from the clearing time you can find the delta CR, which is nothing but delta 1 here. Okay. The second one is, of course, how do you find delta max? That you can find by equating the accelerating areas and the decelerating areas here. Okay. So, we can I will quickly show that on a that is not very difficult. Okay, so this is P versus delta, this is your this of course is P max, this was our PM naught, this was our delta naught. Okay. And now we had that fault, and we have found the delta 1 from the, and this is delta max. Okay. So, now this is simple, this is just a rectangle. So, we have PM naught into delta 1 minus delta naught, this is the accelerating area. Now, this has to be equal to the decelerating area, which is P max cos of delta 1 minus cos of delta max minus PM naught delta max minus delta 1. How do you find this? How did this term come about? The decelerating area come about? This is the decelerating area. It's actually this curve here, it is area under this curve here. It is area under this curve here, this area minus this area. So, what is that? That is just the integral of P max sine delta from delta 1 to delta max. Okay. That will give you, and the integral of sine delta is cos, so that will give you this, rather minus cos, so that will give you this, and then you have to subtract this area from that, which is this part. Okay. So, you just equate that, and from that you will be able to find the delta max, which is a function of both the initial mechanical input and the clearing time. Okay. So, this is a non-linear equation, you will have to solve it using some solution techniques. Okay. Now, we are just going to see the effect of delta max or the variation of delta max with PMO. Now, if for different values, if you clear the fault fast or if you slightly delay the fault clearing, what happens with what happens to the delta max. So, as can be intuitively and from, of course, from mathematically also we have seen, as you increase the clearing time, the delta max goes on increasing. Of course, the PMO is also, the initial mechanical power input is also important, because if that is high, then the delta max will also be greater. Okay. So, here you can see that for a clearing time of 0.5 cycles, that is 10 milliseconds, the delta max is at some, and for a say a PMO of 0.5, you will get around 0.3 or so, 0.32, whereas for if the clearing time is 2 cycles, it is almost double, okay, 0.5 to 0.6 like that, of that order. Of course, this is only a numerical depiction, no fault can be cleared in 10 milliseconds. Okay. Minimum you require 2.5 to 3 cycles, but this is just to show you what will happen if your fault clearing is delayed. So, one more reason why speed is important in relaying. Okay. So, now having this background, we will see what the distance relay sees. Okay. We will, this is what we have seen, oh sorry. Okay. So, now this equation we will derive and then maybe conclude this lecture for today and then continue next time. Okay. So, now our two area system we will start with and see the effect on or rather how the distance relay sees it. Okay. So, this is our one side, the S side, or the, you won't say source because this is a two area system. There are of course a few simplifications here. What will happen if those simplifications or the assumptions are not valid, we will see next time. But for the derivation today, we will use those assumptions anyway. This is the source, this is our relay, this is end A, this is end B, this is I relay or I. In this case, there is only one current, which is I. This is the line impedance, this is the R side impedance, and the voltage here is ER angle 0. So, this is the reference phasor. Okay. Now, we will define two terms for the sake of convenience. That one is the total impedance, which is ZS plus ZL plus ZR. Okay. And the voltage here is at A, we can easily be, or at the relaying point is ES angle delta minus, this is ZS here, and the current flowing is I relay or I. So, this is the, and the current which is flowing is ES angle delta minus here, this is ER. So, I will write it a bit clearly. Divided by the total impedance. Okay. Now, what the relay sees, now I mean this, we have seen the power swing and it from a system viewpoint. Now, we are going to look at it from the viewpoint of the relay. Now, what does the relay see? The relay, for the relay, the apparent impedance as seen by the relay, which is nothing but VA, because this is the relay is connected to the bus A. So, what we get, the apparent impedance as seen by the relay is VA by I. Okay. Now, what is VA? VA is this and I is this. Okay. So, we will simply upon I have just deliberately kept it as I and not replaced it here, because we will use some simplification first. So, initially you will get just this term is just minus ZS plus ES angle delta upon I, which is this. Okay. So, we will ES angle delta minus ER angle 0 into ZT. This is the divider here in the denominator here. So, it goes up here. Okay. This ZT. Now, there is the first of the assumptions that we will make is one per unit. Okay. What happens if they are not 1 per unit? What happens if ES is less than ER, or the vice versa? If ER is less than ES, so we will show in terms of graphs only. We will not derive those conditions, but we will just show in terms of figures. Okay. So, now getting back to our derivation, ZAP is or VA by I. I will use ZAP. ZAP is the apparent impedance seen by the relay, is minus ZS plus this is 1 angle delta upon 1 angle delta minus 1 angle 0 into ZT. Okay. Now, here in this term here, I will divide the numerator and denominator by 1 angle delta. Okay. So, what I will get is minus ZS plus 1 upon 1 minus 1 angle minus delta into ZT, which is nothing but minus ZS plus 1 upon 1 minus cos delta plus j sin delta, this minus and there is a minus outside. So, it become actually this should have been, I have just opened the bracket here, ZT. Okay. So, now we'll do some trigonometric manipulations here, and 1 minus cos delta we will write as 2 sin square delta by 2, and this we will write as j sin 2 delta by 2 cos delta by 2. There is a ZT here. Okay. Now, we will take delta 2 sin delta by 2 common, and what we will get is okay. We just use the, if you are wondering what this is, we have just used 1 minus and sin theta is 2 sin theta by 2 cos theta by 2. Okay. Now, coming back to our equation here, is equal to minus Zs plus Zt 2 sin delta by 2, and we will multiply and divide by sin delta by 2 minus cos delta by 2. So, I am sorry, this is j. So, we will multiply and divide by sin delta by 2 minus j cos delta by 2. So, we will get sin delta by 2 minus j cos delta by 2, and the denominator will be 1. Okay. So, this, if I now simplify further, is Zt by 2 1 minus j, I am sorry, this cot, not cos theta by sin theta. So, it will be cot theta, which is, or cos delta by 2 by sin delta by 2 is cot delta by 2. Now, this is what the distance relay sees. Now, we will now translate this into the Rx plane and see how it looks on the Rx plane. This is R, this is X. Okay. Now, just have a look at the original system here. What is it? This is Z line. Usually, the relay we will see, we are interested only in the primary line, that is. So, we will take the relay at the origin, and this is ZL. Okay. Now, Zs is behind the relay. Okay. So, it is there in the opposite direction. So, it will be here. Okay. So, this is Zs, and after this ZL there is Zr in the same direction of the line. So, they will see Zr here. Now, this will as it is drawn, it has an inherent assumption, is that if you see that the slope of all these ZL, Zs, Zr is the same, which means that the impedance angle is the same. Okay. So, now in a highly meshed transmission system, if you consider that this line is in the part of the transmission network, this could be a reasonable assumption, but otherwise you will get different slopes for Zs, Zr and Zl. Okay. But now assume that they are all in a straight line, which means they have the same slope and the same impedance angle. Okay. Now, we will see how this looks like. This is the origin where the relay is placed. This is the line impedance. I have drawn a slightly higher line angle, but line impedance angle. It is of course very closer to the x axis, but just to make things a bit clear, it is drawn in this fashion. So, now apparent impedance as seen by the relay. Okay. So, what is this minus Zs? Now, minus Zs means from the origin you go behind, this is minus Zs. So, you come to this point. Okay. Then you go to Zt plus Zt by 2. Okay. So, these are two parts. Okay. If you see them, they are I mean, I will write it again here. This is minus Z2, just to make things a bit more clear, minus Zt by 2 and minus, I am sorry, plus Zt by 2 and minus j Zt by 2 cot of delta by 2. Okay. So, now from minus ZS you go to ZT by 2, which could be, which need not be in the middle of the line, which could be anywhere, because it depends on the relative relative magnitudes of ZS and ZR, where ZS and ZR are. If they are equal, then that will be at the midpoint of the line. If they are not equal, then it would be it could be anywhere, and we will see some specific cases next time also, where when we discuss electrical center. Okay. So, now this part is covered. Okay. So, now there is a minus j. So, you go perpendicular, means minus j means there is a turn by 90 degrees, and then you how far do you go? This is ZT by 2 cot of, sorry, again I have written cos, it is cot of delta by 2. Okay. So, this is what, this is the point, the apparent point of the apparent impedance as will be seen by the relay here. Okay. So, we will just join it and see what it is. Okay. Okay. Now, let us see what angle this subtends to the two ends. Okay. It is some angle, say alpha, and since this is the midpoint here, this will be alpha by 2 and this will also be alpha by 2. Now, how is that? We can actually prove it. This is ZT by 2, ZT by 2, this is common, this angle is common. So, we will stop here and continue next time with this discussion.